Light emitting diodes or LEDs is one of the common optical sources that we normally use nowadays. For photonic communication, we require data rate up to 100 to 200 megabit per second, so it is much desirable to use in this range. And with multi-mode fiber, with the value of tens microwatt, LED is the best choices for this type of application. And the normal or the very well-known type of LEDs that we use in photonic communication is surface emitters, or sometimes we call it as front emitters, and the other one is edge emitters. For a simple configuration of an LED given by this gallium aluminum arsenide LED, right? This is double heterostructure LED. Right, we have this kind of configuration or layers, all right, different layers. All right, as you can see, we have metal contact in this side, and in this side we have n-type gallium arsenide, n-type gallium aluminum arsenide, and another gallium aluminum arsenide. Right, and this is the active layer, or also known as recombination layers. And if we take a look at the band diagram, right, the recombination region is the region where the gap is the smallest, right? So it will increase the probability for the recombination to occur here. As you compare with the value of refractive index, right, it is increasing in step, right? And the highest value of refractive index is within the active region, and within this active layer acts as a confined layer, right? Confined of the optical or photon as well as charge carriers, right? The first type of LED, which is surface emitting LED, right? It has this kind of configuration where the photon confining layers is here and the active layer is here. So the photon is produced here and it travel to another layer, and after it travel it will be combined or coupled into fiber, right, directly. And this fiber attached using epoxy resin, right, and it's travel to the optical fiber. And since the photon is produced this way, we refer this as surface emitting LED. In terms of advantages, we have a better coupling coefficient when we couple LED with the fiber system. All right, so we have higher optical coupling efficiencies, and with the configuration we have low optical loss, right, because the carrier recombine near the top heterojunction. All right, we have several materials that we can use for the base material for the LED, especially for long wavelength in terms of optical fiber communication technology. And with this we have higher efficiencies and low to high radiance. The top n-type gallium arsenide contact layer can ensure low thermal resistance and contact resistance, and therefore we have high current densities and high radiation densities. And another advantages is we have internal absorption in the device is very low due to larger bandgap confining layers. And we have reflection coefficient is high, which give good forward radiance. However, in terms of disadvantages, we have this type of LED transmit data slower, or means that less than 20 megabit per second compared to another type edge emitting LED. And it contains short optical link with large numerical aperture due to the configuration. Another type LED, which is edge emitting LED, the configuration or the structure look like this. We have the light guiding layers here, and the rest is substrate and contact metallization, and we need to provide heat sink as well. And the active layer is basically only this stripe. And as you can see, the output beam is Lambert in plane of junction, which is 130 degree, and it is highly directional perpendicular to the PN junction itself at this angle. And with this configuration, we can achieve high quantum efficiencies as well as fast response. In terms of advantages for edge emitting LED, it has superior beam collimation property due to the structure, and we have greater coupling efficiency as well compared to surface emitting LED. We have higher efficiencies with low to high radiance, and it fulfills high brightness LED requirement of the lighting industry. In terms of radiation, it radiates less power to air compared to surface emitting LED due to reabsorption and interfacial recombination due to the structure. And with this configuration, we have a better modulation bandwidth and more directional emission pattern as well. And compared to the surface emitting LED, it offers 5 to 6 times more coupled power into numerical aperture of step or greater index fiber. And this is due to small beam divergence that offers by edge emitting LED. And we have a higher data rate, bigger than 20 megabit per second compared to surface emitting LED. However, in terms of disadvantages, the structure is much complex. We have difficulties or the challenge in terms of to design the heat sinks to get rid of the heat, and therefore it becomes expensive in terms of price compared to other type of LED, and it has also many issues to be handled during the mechanical mounting and installation, so on and so forth. In terms of material, normally we use 3 and 5 ternary and quaternary material. For example, we use aluminum gallium arsenide or aluminum gallium indium phosphide. Alright, with this formula, as you can see, we have X and 1 minus X here. In this sense, we actually can control the amount of material that we put into, and this will effectively control the output wavelength. In terms of spectral width, for surface emitting LED, we have bigger spectrum width. In terms of but for edge emitting, we have smaller and higher intensity of the output power. And in overall, the drawbacks and the advantages of LED, in simpler terms, we have large line width, which is quite big, right? And we have large beam width as well. So with large beam, it is difficult to couple all the signal into the fiber, and therefore we have lower output power. And in terms of electrical to optical conversion, it has lower efficiency as well. However, in terms of advantages, we have a very robust structure or device, and the system is linear, so it's much easier to control